All right, are we ready to get started? Also, if I handed back the first lab to you, double check that there's a grade in Blackboard, because I think I either forgot to enter the grades or something. So just double check that you have a grade for your work, and I should have handed back all the lab ones that I've graded, and I'll try to get those back to you. I have quizzes graded for you as well. They should be in the grade book, and I'll hand those to you probably after class or maybe during class. Try to sneak them in. And then just a heads up, sorry, I'm all over the place this morning. So on Blackboard, I added just to the main content page this paper check-in. And so this is probably just going to be like a quiz grade or something, a nice easy quiz grade. And it's just how's the paper going? And I kind of suggest, turning in 2 sources. And you could either have an outline of your paper or just anything you're thinking, any questions. And when did I have this due? So I put the due date of, February 17th just kind of out there so we can start thinking about it. I don't want you to, of course, leave everything for your paper till the last minute. So hopefully that's on your radar now. Any questions or anything else before we get started? So again, just double check your lab grades, and then welcome to those online. A few people online. And so I know people kind of struggled with MO theory, so just come see me if you want to talk more about it. If there are any questions, I'm more than happy to go over them. But we're kind of going to be shifting gears now, and hopefully this is a little easier for most people, just back to kind of the formulas and hopefully simpler things. And so we're starting with our gas chapter now. And so let's start, well, what is a gas? And so a gas is simply a phase of matter. So if you kind of remember back to first quarter, we discussed solid, liquid, gas, and how, we can see kind of water as our representative form, solid, liquid, gas. Of course, you start heating up your pasta, your boiling water for pasta, and you see steam rising, so there's our gas. And so we can say that gases are merely particles that are moving randomly and very fast in their containers. And so when we kind of talk about this theoretically, we make some assumptions. And so for our kinetic molecular theory of gas, we say that they move in straight lines until they collide with either the container wall or another particle, and we assume that these are elastic collisions, so they're not losing any energy. Obviously, that's not the case. We're not really accounting for intermolecular forces either, just, again, a simplified approach here. So if you have this little bottle, you can seal it up, and of course it would look empty if we just kind of look at it, but then all those little molecules inside would be bouncing around off the walls. And so a gaseous atom or molecule, it exerts a force when it collides with either a surface or another gaseous particle. And so these molecular collisions are called pressure. And so what is pressure? So pressure is just defined as the force exerted per unit area, again by gas molecules as they strike. And so you kind of got a taste of that when you did your water collection lab, and that's why that barometric pressure was important, because we had to kind of account, well, what force did the gas have to act against? And we have our atmospheric pressure that was pushing down right on that beaker of water, so striking that surface. And so just kind of a unit sanity check for everybody. So pressure can be given in pascals, which is equal to 1 Newton over meter squared. You might be familiar with this 1 kilogram per meter per second squared. So that's maybe how you've measured kind of force in physics. And then it would be over this meter squared, so again, over your area. And this would give you 1 kilogram per meter per second squared. So that's what it would translate to in units. And so again, your gas pressure is just the result of constant movement of the gas molecules and their collisions with the surfaces around them. And so this means that the pressure of the gas depends upon several factors. So how many, of course, gas particles are in a given volume. So if you put more gas particles, probably increase the pressure in general. And then what volume of the container. So we'll see kind of how we can change the volume and what effect that has. And then the average speed of the gas particles. And of course, speed is related to temperature. So as temperature increases, that gives it more kinetic energy, which of course makes it move faster. And so again, we're taking kind of a simplified approach when we're looking at this kinetic theory of gases. So again, we said that collisions are elastic, so we're just assuming that these gas particles are bouncing and then bouncing right off. So again, there's no exchange of energy. This is of course not true, and we're not accounting for any sort of intermolecular interactions and attractive forces, just assuming perfectly elastic. And so if there was an exchange of energy, then these would be inelastic collisions. And so you can kind of think of billiard balls. So you hit them and then they bounce, and that's an elastic collision versus inelastic where it might collide. And so we'll look at all these factors. So a gas pressure is dependent, of course, again, on the concentration, and we'll look at this more in detail. So the higher the concentration, the greater the pressure. How many gas particles in a given volume, and so we'll play with that with my little, whatever it's called, thingy-mabobber up there. And so the fewer the gas particles, the lower the force per unit area, and the lower the pressure. Then, of course, if you were to decrease the volume, now you would have, of course, increased pressure from the same amount of particles. And so as volume increases, the concentration of molecules decreases. So we're increasing. So now that same amount has more space. And since the volume increases, the concentration goes down. Again, your molecules would not change in this kind of closed system scenario. And so the other thing is, so we can start to understand the weather a little bit more. And so variations in pressure in Earth's atmosphere creates wind, and changes in pressure helps us predict the weather. And so if you have, and you've probably seen the weather people, they're talking about high and low pressure. And so what does that mean? So if you have an area of high pressure, this is usually associated with clear weather. And then a low pressure indicates some sort of unstable weather, and so maybe a storm is coming or something. And so the number of gas particles in a given volume decreases with increasing altitude. And you may be familiar with that with like hiking. Have you ever heard of the term like, oh, you have thin air up high? So that's exactly what they're essentially saying. So higher altitude, less gas particles with increasing altitude. So that's why they say, oh, the air is so thin. And that's also, why athletes sometimes train at high elevations so they can get their body used to being really efficient with oxygen. And then, of course, when they go back to sea level to compete, it'll be extra competitive. And so, of course, pressure, if you've been in a plane before, or even just driving up and down around the Rogue Valley, sometimes you can get enough pressure difference from the elevation. And so if there is a difference in pressure across the eardrum membrane, the membrane will be pushed out. And so that's what we refer to as our popped eardrum. And you can, again, I'm sure you've felt that effect, either being in a plane or driving around when your ears pop. And so we have, our normal pressure inside the ear, then reduced external pressure, again, as we go into those high elevations. And so that would cause your eardrum to bulge outward, causing pain, and of course causing you to want to yawn or chew gum or whatever to try to alleviate that. And so now let's look at our pressure units. Again, you kind of got a taste for that. And so normally we like to use mercury to measure the pressure. And so what did you notice about just the conversion? Do you remember like when you had to convert between like mercury and water, and what you kind of noticed about mercury?
Is that I think the conversion was like H2O milliliters of H2O was like 13 point something, and then mercury was 1 because it's so dense, and maybe is a little bit more accurate, or.
So, yeah, you're right in that. So we had some sort of conversion. I don't remember the exact number, but roughly for every 13 millimeters that your water moves, only 1 millimeter of mercury moves. So you mentioned the density. So that's exactly it. And so, mercury is extremely dense. And so why people like to use it is it gives you more pressure, more back pressure. And so I've kind of mentioned like using a Schlenk line and all that. Let me pull up a picture because someone brought it up that I forgot to talk about what a Schlenk line is when I was talking about oxygen. Unfortunately, I probably won't find. I need to bug my old lab and tell them to like send me a picture of their Schlenk line. Oh, that's not what I wanted. Go away. So this is at least one example of a Schlenk line here. And so this is what I was talking about, like when they have a trap. And so this little container would be filled with liquid nitrogen. And I often joke, chemistry is a lot of dissolving something in one solvent, pumping it off, and then like adding another solvent. It's really exciting. But so what you would do with the Schlenk line chemistry is, let's say you wanted to, evacuate this. So that's where you would open this up to your vacuum line. So it's hard to tell on this picture, but usually the way these things work is the front manifold is going to be hooked up to gas, usually nitrogen, because it's cheap and relatively inert. And then the back line is hooked up to a vacuum pump, and that's where this comes in. So you can't just suck a bunch of solvent without a trap, or else your solvent would end up in your vacuum pump, and your vacuum pump would be very unhappy. So you have, and then that solvent would also go into the atmosphere. So instead you have this trap with liquid nitrogen, and so it would condense all your solvent that you're pulling off in there, and that's where I mentioned, again, you would not want to have a leak in your system and be pulling atmosphere, because then you would get oxygen in here, plus your solvent, which again was a bomb. But the other thing that you kind of do with this shrink line chemistry is sometimes you have to refill a giant container. And so in order to do so, it's much more advantageous to use mercury, or it has much more density, so it takes a lot of pressure to kind of move it. And so if you have a mercury manometer, you would have like a really tall, like 3-foot little line thing, and you would backfill, so you open up your nitrogen line, and then you would see your mercury kind of creep up as the air went into your flask, your empty flask. So you would have evacuated that flask, and you backfill it with nitrogen, and again, mercury gives you that great pressure. And actually, they're trying to get away from mercury, so there's also special, like little spring stoppers that will stop it and kind of slowly add the air and backfill. Otherwise, what you risk happening is if you were to use like water, for example, you could suck in a bunch of water into your line once you open up the nitrogen, which I've done, because sometimes you can't always use mercury, and it's very easy to accidentally fill your shrink line with water, which is not good. That means your day's over, you take down your shrink line, clean it, and go home. So let's go back to measuring pressure units. And so that's why we have millimeters of mercury then as kind of one of our standards. And so 760 millimeters of mercury is equal to 1 atmosphere. So again, that's 760 millimeters in your column height. That's 1 atmosphere. And so torr is the same thing. So torr and millimeters of mercury are both 760. And so they're used pretty interchangeably. And then we also see atmospheres, or ATM. So this is what we'll want to plug into our formula, PV equals nRT, when we get there. So again, you had a preview in lab, but anytime you're given pressure in something else and you want to use this formula with the gas constant that was provided in your lab manual, so that's being R is 0.0821. I think there's a non-rounded version, but I don't remember that one as readily. So then you'd have to convert. So there's your conversions. And so again, it's saying it's measuring down that atmospheric pressure. And so if you had an evacuated tube, again, your mercury would rise to 760 millimeters with that atmospheric pressure. And so other units that you might see are pascals or kilopascals. So I don't have kilopascals. So kilopascals is just 1,000 pascals. So that would be equal to 101.325 for 1 ATM. So kilopascals. There's also pounds per square inch. So you've probably seen this maybe on your car. So I think cars tend to be around 33 PSI for the tire pressure or so, at least for a regular little car. So that gives you kind of a rough idea. And then again, we had torr, so 760 torr, or 760 millimeters of mercury. And we could also have inches of mercury. So that would be 39.29 inches of mercury. And you could, of course, convert inches to millimeters, get 760. And then we also have bar. So again, this is more like a...
Today is a holiday. Today is a holiday. Today
well,
is
time
a
to go
holiday.
home.
Today is a...
Well, that was really awkward. All right, guys, bye. Anyways, you might see this bar unit, but this is kind of more for the weather, especially like American units. That was the funniest thing. Or, of course, again, 1 ATM. All right, now that we're all either ready to go home or scared, let's see if we can do a little math warm-up. So we said a cyclist inflates her high-performance road bicycle tire to a total pressure of 132 psi. What is this pressure in millimeters of mercury? So I'll give you all a few minutes to work on that. Get your brains going. Remember how to do conversions. I'll try to hand out a few quizzes as I pull out my calculator. So how do we set this up here? We can at least start with what we know and what we're starting with. So we're at 132 psi. We need some conversion factor, and we want to get to millimeters of mercury. So what should I put here? Watching the chat too online. That's exactly what I would do, except I'll put millimeters of mercury towards the same thing. And so yes, we're given these conversion factors here. So right, you could write out your conversion factor too. So right, well, I can say that 760 millimeters of mercury is equal to 14.7 psi. And then exactly like she said, we can plug this in so our units cancel out. So again, don't forget your dimensional analysis skills from first quarter. So now PSI cancels, and that leaves us with, again, millimeters of mercury or either torr on top. And so let's see what our calculator gives us. So 132, and of course, double check my math that I don't enter something in wrong. So divided by 14.7. So then do we get this answer? So I see a lot of nods. So, and we have 3 sig figs. So it looks like we'll round to 6,820 millimeters of mercury. Any questions on that one? All right, so now we'll kind of go through the basic properties of gases and all like the basic gas laws, but then we'll summarize it all at the end, because really all you need to know for this chapter is PV equals nRT, and you can solve everything. But again, we'll get there. And so we have kind of these 4 basic properties of gases and how we describe them. So we can describe their pressure. Again, usually it's given in ATM. That's the standard that you plug into PV equals nRT, but there are other instances where you don't need to put it in ATM. Volume. So again, if you're plugging it into the formula, it's going to be in liters. Temperature. Now this is where it's always in Kelvin, so put a big fat star or whatever you need to do. So you have to convert it to Kelvin, even in the other scenarios that we'll look at that are not PV equals nRT. It must always be in Kelvin. Always, always, always. And so this is really just because of thermodynamics. And so do you guys know what the Kelvin scale ranges from and what it's based off of? I see some no's. Guesses? So it's based off of absolute zero. Have you heard of absolute zero? So what's absolute zero? Saw a lot of nods. Yeah.
When particles aren't moving at all.
Exactly. So complete absence of motion, and that means, right, no little electron running around the cloud. So it just completely stops. So this is just a theoretical point. They've gotten pretty close. I would have to like check back in to see where they're at. I thought they were maybe 0.4 Kelvin or something. So really close, but again, hard to get to true absolute zero. So complete absence of molecular motion. And so because of that, this Kelvin scale goes from, oh, it doesn't have a degree sign, from 0 Kelvin, and of course beyond. And so the key point is that Kelvin doesn't have any negative temperatures. So if you were to use Celsius or Fahrenheit, right, once you get obviously below 0, now we have negative temperatures, and negative temperatures don't make any sense mathematically for what we're plugging in. So if you were to use negative temperatures, your answer would be way off. So always, 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 always be in Kelvin for any of these gas law calculations. So again, star that, always in Kelvin. It doesn't matter what it is, always Kelvin. That is like the #1 mistake students make, is not being in Kelvin. And the last way to describe gases is, of course, the amount of moles. And again, you saw that in lab, where you were able to calculate your amount of moles using all the other information. And so this means that these properties are interrelated. So when one changes, it affects the others. And we'll look at this with these simple gas laws. So these simple gas laws, we're just going to look at relationships between these pairs of properties. And so the simple gas laws are going to be Boyle's, Charles, and Avogadro's, so we'll go through them. And so Boyle's investigates pressure and volume relationship. Charles is volume and temperature, and Avogadro's is volume and moles. But again, we'll go through them separately. Try not to go too fast. And so it started kind of with Boyle's law. And so what they did is they took a little J tube, and you know, look at what a J. I'm going to regret trying to look for a J Young tube picture now. There we go. So this is essentially what a J tube is. So this is more specifically made for like NMR, but the idea is we have this closed system. Oops. It has a little valve here that you can see here. There's a little valve, so you can seal it up so your volume is constant. And so what they do is they can change and measure the volume then at different temperatures. And so they trapped a sample of air in the J tube and added mercury to increase the pressure on the gas. And so what they found was an inverse relationship between volume and pressure. And so kind of looking at their little demo here. So we start with volume. We can have it at 1 liter, and here's our piston that goes up and down. And then if we decrease the volume, so now the volume goes by half, and the pressure doubles. And so let's look at that. Oh, hang on, I'm going to switch my camera work for a second. Here we go. So we basically have the same setup here, and I actually have no idea what this little apparatus is called. I just found it, and it said for use for demos. And so all this is kind of the same concept as we're looking at there. So we have our volume, and you can kind of measure the volume with our little ruler here. And if you need to get up closer and see, you can. I don't think I can show the video to y'all with my setup. So we have, and then our pressure is measured here. So I just set it to 1, and it's at 8 centimeters on this marking. So then if I turn this knob, so you can see, and again, you can get closer if you need to, otherwise the video should be capturing it. And so now I'm going to decrease it down, and so again, you can see that pressure slowly rising. And so once I get it to just about 4 there, so I went from 8 to 4, and you can see how the pressure went from 1 to 2. So I halved the volume, doubled the pressure. And then, of course, now we're going to have to wait forever. So let's see if I can take it all the way to 16. I'm just going to fall off this. Go, go. You can see that pressure dropping. And so again, now it's at about 16. So I went from 8 to 16. Now the pressure's roughly about half there. Again, that's about what we expect. So then we can go back, and now we can understand the math. And so again, Boyle's law states that the volume of a gas is inversely proportional to the pressure. And so as we decrease the volume, that forces the molecules into smaller and smaller spaces. And so what do you notice, though? Let's just talk about, so what happens here? So what's going on as it kind of plateaus out? And what do you know about kind of real-life gases, too? And then, but then why does it just kind of plateau out here? Slash, what happens to gases as they get pushed closer and closer together?
They turn into solids.
Yeah, so they turn into liquids or solids, and so we do eventually reach right, the physical limitation. We can only pack them in so much, and so that's why it kind of plateaus out. And again, going to be turning into liquid or solid. So, right, solid, a good example of that is your CO2s, aka dry ice. So there's all the way down. Yeah, I mean, you can compress any gas. I'm not sure like what you would have to compress neon to, because I haven't seen like liquid neon readily, but you see like liquid nitrogen pretty commonly, or like liquid helium. But I think that's just more like no one orders that much neon that they get it to a liquid form normally, but and so again, our pressure of our gas is inversely proportional to its volume. And so again, as pressure increases, volume decreases by that same factor. And so the formula that you'd want to use for this is P1V1 equals P2V2. So I would write that down. And so that's also why diving. So does anybody dive in here or like have scuba certification? So let's look at diving. And so for every 10 meters of depth, a diver experiences approximately 1 additional atmosphere of pressure due to the weight of water. So you can first imagine that. So at 20 meters, a diver experiences approximately 3 atm of pressure. And so if a diver holds his breath and then rises to the surface quickly, right, you can imagine, so then, right, you have your pressure and your air at under 3 atm of pressure. So if you were to rise really quickly, those gases could essentially explode. But really what you know too, so they tell you to rise slowly and be exhaling constantly as you're going up. And then you also want to, again, go slow because you also have, right, all the gases in your bloodstream as well. So you have, right, those little oxygen molecules running around and CO2. So of course, if you rise too quickly, there's also the risk of that gas expanding. Yeah.
So I've heard that when you're diving and you're coming back up, if you go too deep, you get like nitrogen poisoning or something like that. Is that why?
Yeah, so that would be like, because again, you know, nitrogen is a huge component of air. It's like 78%, I want to say. So yeah, if you go like too quickly and then all that nitrogen is expanding too much, that could overwhelm, you know, the oxygen, and then you don't have enough oxygen. So yeah, all that leads to it. So that's why you go, again, slow, exhale while rising, and that's why you have to be trained, so you know what to do and know how to do it safely. So let's do another little practice, and I'll try to hand out some more labs. So as you breathe, you inhale by increasing your lung volume. And maybe you've seen that in biology, like how your diaphragm kind of works like a balloon. So all your diaphragm is doing is increasing your lung volume, and that's essentially, right, decreasing the pressure, and so now air can go in. And so a woman has an initial lung volume of 2.75 liters, which is filled with air at atmospheric pressure of 1.02 atm. And she increases her lung volume to 3.25 without inhaling any additional air. So you're basically saying, you know, what's the pressure right before that air rushes in? So you're imagining, okay, the diaphragm's expanded, ready to inhale. So what's going to be the pressure in her lungs? So I'll give everyone a few moments to do that. So you should have something set up. So I just rewrote the formula. P1V1 equals P2V2. And so this is one of those scenarios where I was saying, like, it doesn't quite matter what the units are. So they gave it to us in liters, so probably just leave it in liters. But if it was in milliliters and milliliters, that would be fine, because we're just kind of comparing and not plugging it into the big formula with our gas laws. So those units would cancel. And same thing with the pressure. They gave it to us in ATM, so you might as well just leave it in ATM. But if it was in like torr or PSI or anything else, as long as the units were the same, doesn't matter too much. And so now we just have to make sure we put in, right, our initial conditions. So 2.75 liters times 1.02 ATM is equal to 3.25 liters over volume V2, or X. And so what do we get for our answer? What do we get? Go for it. 0.86, is that what other people got? I see nods. I can punch it in. So that looks excellent. And so that makes sense, right? So we expect it to be a lower pressure, and always do a little sanity check on yourselves. It's easy to punch something in wrong on the calculator. And so you're just kind of saying, well, yes, that makes sense because my volume increased, so I'm expecting that pressure then to decrease. And so we have 3 sig figs in here. And so we'll report it to 3 sig figs, so 0.863 ATM. So questions about this so far? Now let's look at volume and temperature. So we have volume of a fixed amount of gas at a constant pressure increases linearly with increasing temperature, again in kelvins. So star that again has to be in kelvins. So volume and temperature have a direct relationship. And so again says the volume of a gas is directly proportional to the absolute temperature. That just means in Kelvin. And so according to kinetic molecular theory, when we increase the temperature of a gas, the average speed and, of course, kinetic energy of the particle increases. And the greater volume spreads the collisions out over a greater surface area, so the pressure is unchanged. And so this would be our relationship. And so, of course, if we extrapolate, we can see that they end up at 0, but obviously all gases condense into liquids before we get down to 0 Kelvin. And so let's look at this. So we'll look at this with a bit more extreme. And again, when the temperature of the gas increases, the gas particles move faster. And so that means collisions are more frequent. And so if there's more force exerted, then the only way for the pressure to remain the same is for the gas to occupy a larger volume. You can do the opposite, or we'll do liquid nitrogen in just a second. So we have a filled balloon is moved from an ice bath to a boiling water gas bath. Then we'll see the volume expands with the balloon, again, moving, the particles moving faster due to increased temperature. So let's look at this. Let's start with our balloon. So we have our balloon, so I'm going to blow it up. And I'm not going to do it too big, or else it won't fit. And so right now, oh no, there's a hole in this. Okay, where's my other balloon? I think I grabbed 2 balloons. Let's try that again. that one will fit. So we have our balloon, and first of all, right, we can think about all the pressure that it's exerting right now. So there's, of course, molecules of gas in there. And let me draw this out. In hindsight, I should have made some more scenes for this. But right, we have our balloon, so we filled it up with air. And so you can imagine, right, everything that's holding it up and keeping it filled under the atmosphere is all those molecules of air that I just blew inside. And so you have to imagine, right, the balloon, it's inflated because it has all these molecules in there, so they're moving, right, they're keeping it inflated against the force of the atmosphere. And so now what happens when we slow down the kinetic speed of that? So let's switch. Sorry, doing camera work too. Going over liquid nitrogen. Trying to crack my balloon. There we go. So now it's, well, it was small, and of course now it's heating up again. And so as it heats up, it expands. So you can repeat it, right? Cool it back down. So we haven't changed the number of moles or anything. It's a closed system. Do that one more time. And so we can also do this with marshmallows. And yes, I know we have at least one vegan in the room. Anybody else vegan? Huh? Just you? Two? Two vegans? Okay. I'm just making sure that everyone's included.
Good looking out.
Huh?
Good looking out.
Yeah. So let's see what happens. We can eat these. So I don't know how much they'll shrink. My other tool. And whoever wants to be my first guinea pig. You can eat them, and you should get like dragon breath a little. You pop them in your mouth. And you can come up if you want marshmallows. I got plenty of marshmallows.
I don't think I've ever eaten a frozen marshmallow before.
Yeah,
It's like Lucky Charms marshmallows, but better.
Marshmallows. Yeah, your hand. Some marshmallows.
Tastes like marshmallow?
They didn't really shrink. I was hoping they would shrink, but play with more marshmallows.
Right.
They need the bigger ones.
Yeah, let's try. You want a big one?
I do, yes.
This is really also just like eating marshmallows and playing with marshmallow time.
But that's the timing chemistry.
Marshmallows. Okay, you wanted a big one?
Big one.
I don't know, it didn't shrink at all. Okay, go for it. You want a small one, big one?
Oh, I don't care, whatever.
I.
Well, I don't know if there's seconds.
Put them where I can see them.
Oh, you want a big one? Yeah, okay.
I would also like to try a big one after everyone's had one.
Or is it just liquid nitrogen?
I don't think a freezer will freeze it enough.
That's what I was thinking.
Because you should get some dragon breath. Marshmallows.
It's so cool. Thank you.
Technology.
Yeah.
Whatever's happening on your iPad is not what happened on my laptop.
I sent it to me an email. See, here we go.
Alright, anybody else need marshmallows? Oh yeah, do you want a big one or a small one?
Take a big one.
Oh yeah, go in for the big one.
And what's delicious?
Alright, there are plenty of marshmallows. No, we don't need more marshmallows. So let's see if we can get marshmallows to demonstrate the other. Wow, that was too big. Oops. Now I'm just throwing marshmallows everywhere. So if I put them in here and apply a vacuum, this isn't working that well. I was hoping they would expand more. They don't look like they are. Up, up, you see that? Yeah. Now they are expanding and they shrink down. So. Anybody need to eat any? Anybody need more marshmallows?
Yeah, I was gonna drop them
That's
for
school
both.
right now.
You want small ones or big ones?
I don't discriminate against my.
The little ones are so much, they're like the Lucky Charms marshmallows.
Exactly.
But. There's something you can sign to be like, get MRSA or liquid nitrogen. Oh, really? Fast. So I have it right here. It's not hard.
I don't know, you can always start with Dusty, like,
I don't.
yeah, we need
I didn't
like
see it.
so we can eat marshmallows all day.
Oh, it's.
Crunchy
that's why.
marshmallows.
Marshmallows?
That's why I couldn't find it. Is that point? Okay, I have that number written down, but then I was like, where is this?
All right. Oh, yeah, you two can take the bag if you need, I think.
No chance to grab the.
Go for it. Do I need to pass around marshmallows just for people to eat? Yeah, they can make their way around. If anyone needs frozen ones, I'm more than happy. Yeah. I'm not entirely sure like how freeze-dried works, but yeah, because I thought that was like some dehydration process too. But yeah, I don't actually know. Now I am kind of curious. And while we eat marshmallows, so there's a great YouTube video that kind of shows the same effect. If I can find it. I like this one. Hang on, I think.
Hi everybody, I'm meteorologist Jay Burschback along with Carl Nelson at the Imagination Station. Today we're dealing with one of my specialties, air pressure, the power of air pressure. And you may have seen this experiment before using a gas can or a smaller can. This is big scale. This is the Imagination Station's version of supersizing that experiment, showing air pressure which can crush this huge barrel. Carl.
So we got a steel 55-gallon drum here. And I just want to give you a sense for how strong, how rugged these barrels are. Jay, if you could stabilize the barrel, I'm going to take a sledgehammer and try to... If you relied on me to crush this barrel, we'd be here all day.
Sure.
Because that thing is pretty tough. So instead, like you said, we're going to use air pressure to crush this drum. So let me flip this up. I'm just going to stick it on its end here.
On its end? Oh, okay.
Because what I'm going to do first is add some water inside. About 6 cups of water. And what the water is going to do is we're going to create water vapor inside that we're going to heat up. Now, water vapor, when it's warmed up, and air, when it's warmed up, occupy a little bit more space. Our goal is to try to trap some of that expanded air and water vapor inside. We're going to seal this up and then cool it down.
Okay.
We should see some crushing action at that point. But first, we're going to need to heat that air up.
Okay.
So help me flip this up on our stand here.
Okay.
The thing we're looking for, Jay, is we want to see a nice, solid stream of steam coming out this opening here.
Sure.
And in order to do that, we can't just use like a blowtorch or anything small. As this is the supersized version, we're going to use one of these road torches.
Yeah, I think I'll back up.
All right. So it'll take a few seconds here to get the water warmed up inside the barrel, but to give you an idea how big the flame we're going to work with. See, there's a good sort of jet of steam shooting out, but we're going to try to capture that
Okay.
by putting the plug back in. We're going to wrench it down tight because we don't want any of that warm, expanded air to escape. But the key now, Jay, is wheel over that tray of ice. We're going to cool this baby down really quick in a tray of ice. Hold on. I'm going to just spin it down. Rotisserie. Well, the first thing we should hear are a couple of ends of the drum popping in.
There we go.
A couple of the ends going in. There's the other end. There we go.
There we go.
Give it a second.
So what we're seeing is air pressure literally crush.
14.7 pounds per square inch of normal atmospheric pressure are now pushing down on this drum, and because that water vapor inside and that warm air inside
There it
has
goes.
cooled down, taking up less space, doing a lot more damage than that sledgehammer did earlier.
That is
to the drum.
amazing. Looks like a pop can or a soda can.
Looks like a pop can or a soda can, or if you've ever rinsed out plastic milk jugs,
Sure.
and then you put the cap back on with warm water, stick it on the counter, you can see after a time they start to like collapse back in. Same principle, but it's a safe, at-home way you can do it.
Sure. Yeah, no one, having that blowtorch,
blowtorch is
for the
probably
experts like you.
All right, so again, that was same concept as just sticking the balloon in. It was just a little more extreme since they actually heated it up, right? So they got the vapor pressure to take up a lot less space of the water. And then, of course, they cooled it down with just ice, condensed back down. That water probably converted it back to liquid. And, of course, now that there was not enough molecules, right, to keep it basically, right, inflated against the pressure of the atmosphere, it was crushed. So again, we saw that with the balloon when we put it in, and it just was crushed down as we condensed that gas inside. All right. Any questions about that? And so our formula is going to be V1 over T1 is equal to V2 over T2. And so now let's practice the math for it. I'll rewrite the formula. So V1 over T1 equals V2 over T2. And again, in this formula, it doesn't matter so much that your volume is in liters. Obviously, they're giving it to us in liters, but if it was in milliliters and milliliters, that would be fine. It's just temperature has to be in Kelvin. So has to. So see if you can do this example. while you work on that, I'll hand out your homework. And at the end of class, I'm more than happy to freeze more marshmallows for people.
How do we get our hands on some of that?
I think you just have to like order it from, I think we go through an industrial source, and then you would want like a little dewar or something. That's probably the most expensive part initially, is just getting a dewar to hold it in.
What's it
I-
called?
A dewar? I think that one's too small. I would go with like a 4-liter dewar. If you get a 4-liter dewar, that's enough to make a batch of liquid nitrogen ice cream. Yeah, that's what I want to do. Yeah, that's just like not enough. I'm down with the soap one. The ice cream we need to change though.
Anything extra on it?
Although I think Grant's Pass might have a bigger dewar. So maybe if I got the dewar, then we can make ice cream.
Do a CHEM bake sale.
I know, we could totally raise money. Who wants to start a science club or chem club?
I would totally.
What would be the process of making ice cream?
Like literally you just take a stand mixer and start pouring liquid nitrogen on it. Or you could do it like a hand mixer. But you just want it to mix fast, and it's just like making regular ice cream, you know, cream, milk, sugar, whatever you want.
And then you put the liquid nitrogen in it?
Yeah, so you just like literally pour it in there, but then it's stirring so fast. And it comes out really nicely because you get like small microcrystals with it freezing so quickly. So you get nice smooth ice cream. And it's like one of the only ways to make boozy ice cream since it gets it cold enough.
So you wouldn't get any like extra liquid nitrogen, like freeze off your top or anything?
I mean, and not if you mixed it well, like in the ice cream. So that's why I recommend using either like a stand mixer or an electric hand mixer so you can mix it really well and you don't have, little frozen bits. And you kind of, have to watch it, like pour some, stir it, check the consistency, keep kind of pouring. But I know from experience that like about a 4-liter dewar will give you a nice bowl of ice cream, but that's just too small.
What kind of burns would that cause?
It's just like a little, like, burn. Like, I mean, they use it to like burn off warts, right? Or if you get a little burn, it'll probably like make a blister. So it's not like that bad, but yeah, like you could dip your hand really quickly into liquid nitrogen. Like, I don't want to do it, but like it freaks me out, even though I know it's physically possible. But yeah, you just don't want it to like pool anywhere on you, because then that will cause a burn. And obviously, if you like leave it submerged for too long, it'll cause it to freeze. All right, what do we get for our answer, or what do we do for our setup? So hopefully we had something. This over at unknown temperature is equal to 2.57 liters. And then what's 0 degrees Celsius? What's that in Kelvin?
273.15.
So 273, if you really want to add the 0.15, that's fine. I usually just leave it off because it never makes that much of a difference. And so then we cross multiply, divide. What do we get for our answer? And so sanity check. What do you think? That should the temperature probably be higher, lower? Just before we even punch in the answer. So we have the gas, right, at a 1 volume, and then we say the volume decreases. So do you think the temperature should be higher or lower than 0?
Higher.
So higher, and so that's what we get. So again, just always do a little sanity check for yourself. Does it make sense with what's going on in the problem? And then, our answer matches what we were thinking. So did we all get 297 Kelvin, roughly. And then what is this back in Celsius? What did you say? So 24 equals 24 degrees Celsius. So just subtract 273 from that. Any questions about that one? So now let's look at Avogadro's law, and then we'll try to sum things up, but may have to continue on to Thursday. And so I feel like this one is pretty self-explanatory, or at least it makes sense, right? So volume and moles have a direct relationship. You kind of saw that as I was trying to blow the balloon. So of course, the more moles of air I was blowing in, the bigger the balloon was getting. And so volume is directly proportional to the number of gas molecules. And again, we're assuming pressure and temperature are held constant. And so it makes sense. More gas molecules means that they would have to occupy a larger volume if our pressure and temperature are being held constant. And this is also super key. And we'll look into more relationships probably on Thursday because we're running out of time. But equal volumes of gases contain equal number of molecules. So the gas doesn't matter. So that's super important and kind of helps you. So again, doesn't matter. We saw that with our moles. So we can always calculate our moles. And so this means we have a relationship here. V1 over N1 equals V2 over N2. And so again, all that is saying is that the volume of gas is directly proportional to the number of gas molecules. And so of course, if we increase the number of gas molecules, that means we're having more collisions. So if the pressure is being kept constant, then the volume has to increase. So let's see if we can do this really quick, and then I'll give you a preview at least to how you don't have to memorize anything but PV equals nRT. So we have an athlete in this kinesiology research study has a lung volume of 6.15 liters during deep inhalation, and at this volume his lung contains 0.254 moles of air. Then he exhales, and the lung volume decreases to 2.55, and then so watch the wording on this problem. How many moles of gas does the athlete exhale? So I'll give everyone a couple of minutes to do that. do we set up? So V1, N1 equals V2, N2. And so let's see, so it said that he had a lung volume of 6.15 liters, and that had 0.254 moles. And then so the lung volume decreased to 2.55. And so let's see how many moles then were in the lung, right? Because this is what's in the lungs still. So that was kind of the tricky part of this question. And always double check my math. So did we get 0.105 in the lung then? I see some nods. So this is 0.105 moles in lung. But the problem asks, well, how many moles of gas does he exhale? So then we just have to take the difference. So 0.254 minus 0.105. And so how many moles were exhaled? What did you say? 0.149. Perfect. 0.149 moles exhaled. All right, so now we have just enough time, I think, for a quick derivation. So I keep saying all you need to know is PV equals nRT. And so let's look at that, because that's totally true. So we just went through a bunch of formulas, but we can rederive all of them with PV equals nRT. And so by the way, if you were to type into like gas constant to Google or Wikipedia, you would get this mess of answers. And so that's why I always say liters, ATM, Kelvin, and moles. So this is a gas constant that you're given in lab. I just rounded it to 0.0821. I think your lab rounded it to 0.08206 or something like that. But this is what we're looking at. And so again, this is when we're using these units. When we move on to like thermodynamics, we'll switch to this R if we're working with joules. But that's where it comes from. So it all depends on what unit you're working in. So when you look at this, don't panic. Just look for what we always work in. So liters, ATM, Kelvin, moles. That's why I just stick with that so we can be consistent with our gas constant. And so that means, right, R is our constant. And if R is a constant, that means you can set everything equal to that. So P1, V1, and then move this over to the other side over N1, T1 is equal to R. But then it doesn't matter what this is, right? So we could have a second set of conditions. So P2, V2 is equal to N2, T2, and that's also equal to R. And so that gives us this relationship. P1, V1 over N1, T1 is equal to P2, V2 over N2, T2. And now you can get back at all those formulas that we just went through, the P1, V1 equals P2, V2, by holding the other variables constant. So that was when we held moles constant and temperature constant, so those just went away, leaving us with that. We were looking at, volume and temperature, holding pressure and moles constant, so those cancel out. And then we looked at volume and moles, again holding pressure and temperature constant, so those canceled out. And so again, all you need to remember is PV equals nRT. And then you might need this for other scenarios where, let's say they're changing pressure, volume, and temperature, but not moles. So then you could get rid of moles. So if N constant, right, that gives you back P1, V1 over T1 equals P2, V2 over T2. Or, you could even change all the variables and have to use that relationship. So does that kind of make sense? So we'll do some more practice with this tomorrow, or Thursday. I think we're out of time or running out of time for today. And so you should have gotten your quiz back and your lab one back if you were present in here. If not, come see me and I have it. And again, double check your Blackboard grade and make sure everything's entered in properly. And I didn't accidentally forget to enter you. All right, and I will see half of you in lab in about 30 minutes or so for our TLC lab. Should be pretty fun. Otherwise, I will see y'all on Thursday. Any questions in the chat before I end the stream? Thanks for joining. Thank you. Oh, you're fine. All right, I'm going to go ahead and end the stream. Thanks for tuning in.